Since the birth of modern chemistry, scientists have sought to better understand chemical reactions at a more fundamental level, why they happen, how to predict them, and how to control them.
In chemistry, actually, all chemists really cares about what kind of product we can make from the original chemicals. Why every chemical reaction behaves very differently. Actually, this is a very big challenge to understand that. Chemical reaction dynamics is a field that tries to understand the chemical reactions at atomic, molecular, and even quantum level.
Tools and techniques developed by Xueming, a professor at Southern University of Science and Technology and a research fellow at Dalian Institute of Chemical Physics, Chinese Academy of Sciences, enable scientists to deduce how reactions proceed at their most fundamental level and in unmatched sensitivity and resolution. In 1935, Henry Eyring and Michael Polanyi founded modern reaction dynamics by proposing that the key to any chemical reaction lies in understanding its extremely brief transition state, lasting only quadrillionths of a second, during which new bonds are forming between atoms while old ones are breaking off.
So the concept proposed by Eyring and Polanyi is this transition region called transition state really decide what kind of chemical reactions it is, like how fast of this chemical reaction occurs, what kind of product can be made from these chemical reactions. So this really becomes a very important research field, try to understand the transition state.
In 1967, 1986 and 1999, 7 chemists were awarded Nobel Prizes for developing tools and experiments that could piece the processes together. Continuing in this tradition, Professor Yang has developed new generation molecular beam techniques for studying reaction dynamics, including a powerful method called quantum state-specific backward scattering spectroscopy for probing reaction resonances. They involve crossing 2 well-defined beams of molecules in a high vacuum and observing the scattering of chemical products with a quantum state resolution after they react.
2 beams cross and look at the scattering product in space and with quantum state resolution. So this requires actually molecular beam machines with a high vacuum, very advanced lasers, and detection techniques, which allows us to probe a specific chemical reaction at all the details of this process.
With so much detail in his observations, Professor Yang and his colleagues have been able to develop accurate physical pictures to describe intriguing quantum aspects of transition states in chemical reactions. He has made key contributions in the study of 2 important quantum chemical phenomena: quantum reaction resonances and geometric phase effects. When developed further, reaction dynamics promises improved simulation and control of reactions. Chemists should be able to predict the properties of individual chemical reactions to simulate complicated chemical processes and even custom-make chemicals with specified properties using controlled reactions.
If we can predict every chemical reaction, its chemical reaction rate, how fast it is, and how that occurs, and we can really understand every chemical reactions that way, then I think chemical science will become a more accurate science, a more hardcore science, I will say. We can develop processes to control these chemical reactions.
The instruments and experiments developed by Professor Yang and the discoveries he has made with them are expanding the field of reaction dynamics broadly and deeply to an unprecedented level. For developing new generation molecular beam techniques with high resolution and sensitivity for state-resolved reaction dynamic studies, revealing quantum resonances and geometric phase effects in chemical reactions, the 2022 Future Science Prize in Physical Science goes to Professor Xueming.